So far we have learned about 5 mathematical representations for regular languages, and they are deterministic finite state automata DFA, non-deterministic finite state automata NFA, NFA with epsilon transitions, regular grammar and regular expressions. So these are the 5 representations that we have learned: DFA, NFA, epsilon NFA, regular grammar and regular expression. And we, after discussing each representation, we learned algorithms for converting one representation into another. We saw that all these representations are such that they are pairwise equivalent, meaning given one of the 5 representations, say N of A, we can use an algorithm to obtain any of the other representation. So given one of the 5 representations, there exists an algorithm to convert the given representation into any one of the other 4 representations, and that is what we learned till now in this course. And today we are going to discuss about closure properties of regular languages. And before we define closure properties, we can see when we say that some operations are closed on a set, we can start with an example. Consider the set of natural numbers, and we can see some example operations closed on the set of natural numbers. The first one is the increment operator. And why is it that the increment operator is closed on natural numbers? Because for all natural numbers n, if n is a natural number, then n plus 1 is also a natural number. So the result of performing the increment gives you a natural number, and that's why the increment operation is said to be closed on the set of natural numbers, because the result is again a natural number. Another example is addition, because for all natural numbers a and b, if you add them, you are getting a natural number. So if the result of performing the operation is again in the set, you can say that that operation is closed on the given set. Now examples of other kind of operations which are not closed on natural numbers. First example is decrement. And why is it that decrement is not a closed operation on the set of natural numbers? Because you can find a natural number on which if you perform the decrement operation, the result is not a natural number. For example, if you consider 0 as the least natural number, then what is 0 minus 1? It's not a natural number. So decrement is not a closed operation. Another example is subtraction, which is not closed on n, because you can find 2 natural numbers a and b such that a minus b is not a natural number. And if you find any ab where a is less than b, this is the case. I hope it is clear. An operation is said to be closed if the result of performing the operation is again in the same set. So you can define it as a set S is said to be closed under an operation O if the result of performing the operation O on the set S result in an element of S. So that is the definition. This is now enough to define the closure properties of regular languages. Note that language is a set of strings. So basically a language is a set with a number of strings in it. So it's a set. So when we say operations, we are going to look at set operations like intersection, union, complementation, etc. So what is a closure property for a regular language? The operations under which the set of all regular languages are closed are called closure properties of regular languages. That is, if you consider a set operation such that if you perform a set operation on two regular languages, and if you are getting always a regular language, you can say that that operation is a closed operation. And here are example closure properties. First one is string reversal. That means if you take a regular language, it is a set of strings, and take the reverses of all the strings in the given language. Take the set of all string reversals, and we are going to prove that the new set, that is the set of all string reversals, is again a regular language. Second property is complementation, meaning if L is a regular language, its complement is again a regular language. Third one is concatenation, meaning if L1 and L2 are two regular languages, then the concatenation of L1 and L2 is again a regular language. Fourth one is Kleene iteration, meaning if L is a regular language, then the Kleene iteration of L, that is L star. Hope you remember the definition of L star, which is L raised to 0 union, L raised to 1 union, L raised to 2 union, etc. So Kleene iteration is regular, again a regularity preserving operation, meaning if you perform that operation, the resultant language is again regular. Then intersection is also a closed operation, and finally union. And in this class, we are going to discuss about the first four closure properties. So closure property means if you perform that set operation, the result is again a regular set. First consider string reversal. We can try to understand it using an example. Here is an N of A given. Can you see what language is represented by this N of A? In order to accept a string, you have to start in the start state and you have to go all the way to the final state. So the first symbol must be A and the last symbol must be B, and in between you can have any string of A and B. So the language can be mathematically written as set of all strings starting with A and ending with B. In between you can have any string. Now you consider another automaton which is obtained from this. Can you tell me what I did to obtain this automaton from this? Exactly the same set of states. What I did is, I did three things to obtain this. First thing is, I reversed the directions of the edges in it. Here this edge is going from left to right, I did it from right to left. So I just reversed the direction of edges. Here it is like this and reversed it. Okay, but this doesn't matter for a self loop. And here again it's going from left to right, here it is right to left. So I reversed the direction of edges in the N of A. That is the first step. Second step is, I made the initial state of the given machine a final state, and that is the second step. I changed the initial state into final state, and the last step is I changed the final state of the N of A into the initial state of the new machine. Okay, forget about what I did. Can you tell me what language is represented by this N of A? It's easy to see. It's starting with B and ending with A. So you can write it as this. So in this particular case, this N of A is giving you the reverse of the language represented by the given N of A. For that, what I did is, the same set of states, I have reversed the directions of all the transitions or edges and interchanged the initial and final set of states. And that's what I did. I hope you followed. It's a very simple example. You can try it for any other N of A. So now we can try to formalize. How can you prove that the reverse of a language is regular? So this is the formalization. Given an n of a, capital A is a quadruple, capital Q, capital S, capital delta, capital F. Recall that in an n of a there may be one or more initial states. In this example only one, but in general there could be any number of initial states and set of final states. Not that the second one in the quadruple represents the set of initial states and the last one represents the set of final states. It's very important. So given such an n of a over an alphabet set sigma, one can construct an n of a b from this with the same set of states. In the new machine, the set of start state is actually the set of final states of the given machine. So given machine's final states becomes the initial states of the required n of a. And transition function is new, we will define it here, and the set of final state is nothing but the set of start state of the given n of a. So we interchanged the set of start states and set of final states to get the new n of a. The only other change made is you reverse the edges. So the new transition function delta prime is nothing but the transition going from qj to qi on a if there exists a transition which is going from qi to qj on a. So now you are adding transition from qj to qi when you have a transition from qi to qj. So you are just reversing the edge. That's what you did. This is how you mathematically write it. And if you do that, you can prove that the language of the constructed n of a is the reverse of the language of the given n of a. And the soundness and completeness of this construction can be proved using the principle of mathematical induction. So this theorem tells us that given an n of a, you can construct an n of a to accept the reverse of this language. So there exists an n of a for the reverse of any regular language. And hence we can conclude that regular languages are closed under string reversal because the reverse of any regular language is regular. Okay, with that let us proceed to the next closure property, which is complementation. So we need to prove that the complement of a regular language is regular. So given an n of a or a d of a, we need to construct a d of a accepting the complement of the language. That is our objective. Here again, consider an example. So here is an here is a d of a given to you. So can you tell me what kind of a string is accepted or what is the language? You can see that you will reach into the final state only if you have the substring AB. So if AB is there, you are getting into the state. After A will let you stay here. So the moment you process the first AB, you will reach into the final state and stay there forever. So the language is the set of all strings with AB as a substring in it. Now you consider this DFA that I obtained from this. Can you tell me what I did to obtain this? The same set of states, I did only one step, that is interchanging the final state status. I made all the final states non-final. Q2 is a final state here, so in this I made Q2 a non-final state. Q0 and Q1 are non-final states in the given machine, so in the new machine I made both of them as final states. So what I did is I changed all the final states to non-final states and all the non-final states to final state. I made a final state non-final and I made all the non-final states final. That is what I did. So now can you tell me what language is accepted by the obtained DFA? You can see that is exactly the complement of this language. So if AB is there, you will come to this and you will end up there. You cannot escape. So if AB is there, you reject. If AB is not there, you accept. So it happened to be a DFA for accepting the complement of this language, and this is in fact true. So given a DFA, you can obtain the complemented DFA by making all final states non-final and making all non-final state final. Okay, so we can now formalize. Given a DFA, capital Q small s, not that for a DFA only one start state, that is small s. Capital Q, small s, small delta, capital F, or an alphabet set sigma like AB, one can construct now the DFA B from A said that B is having the same set of states, the same start state, the same set of transitions. The only difference is the final set of states. What is the set of final states here? Q minus F. That means whatever states are there in the given machine as non-final, you made those states as final. Okay, and whatever state is there as final, you have taken it out of Q. That's what you did. So you made all non-final states final and you made a final state non-final. And this is how you will write it mathematically. And you can observe that the language of this newly constructed DFA is the set of all strings minus the set of strings accepted by the given machine. That is exactly the complement of the language accepted by the given machine. And here again, if you want, you can use the principle of mathematical induction to prove the correctness of the construction, that is soundness and completeness. And with this, let us move on to the third property, which is concatenation. So we are going to prove that given two regular languages, L1 and L2, the concatenation of them, that is L1 concatenated with L2, is again a regular language. Here the proof is easy. We can first have the claim. Given epsilon n of x, I am assuming that given language is regular means I can, without loss of generality, we can assume that there exists an n of a with epsilon transition for each of the languages L1 and L2. And if you recall, we learned that we can obtain an epsilon n of a with a single initial state and a single final state for any regular language. If you don't remember it, please go back and see from that lecture. For any regular language, you can have an epsilon n of a which is having only a single initial state and a single final state. So here, I assume that L1 and L2 are regular, hence there exists two epsilon n of a's for L1 and L2. Then you can construct an epsilon n of a, third one, over the same alphabet such that the constructed n of a is giving you the concatenation of the languages L1 and L2. Suppose you are given with these two. So L1 is regular, then we can assume that there exists an epsilon n of a, say A1, with a single initial state and a single final state. Similarly for L2 you have. And in a proof we have discussed a very similar one. So how will you construct the NFA with epsilon transition for the concatenation of these languages? The only thing you have to do is this. So what I did is I removed the final state status of this and then I made an epsilon transition from this state to the initial state of the other machine. And suppose now the new machine accept. How will you accept? Going from this initial state to this final state. And if you are doing this, then this part of the string is in L1. And this part of the string is in L2. So whatever is accepted by A3 is a concatenation of a string, one from L1 and another one from L2, that is of the form XY, such that X is from L1 and Y is from L2. And now suppose that XY is a string such that X is present in the language L1 and Y is present in the language L2. Then there exists a path from S1 to F1 for X because X is in L1. And there exists a path for Y from S2 to F2 because we assume that Y is an element of the language L2. Then by using this transition you can accept X followed by epsilon followed by Y, that is XY, and that is the soundness of the construction. So soundness and completeness of the construction. So this is fairly easy to see. And let me proceed to the last operation that we are going to see in this lecture, which is Kleene iteration. That is, given a language L, we need to construct an automaton for L star. And here is the claim. Given an epsilon n of A with a single initial state and a single final state, say for a regular language L over an alphabet set sigma, then one can construct an epsilon n of A prime over the same alphabet set sigma such that the language of the constructed n of A with epsilon transition, that is A prime, is the Kleene iteration of the language L. So L star is, if you recall, it's L raised to 0, union L raised to 1, union L raised to 2, etc. So that's what the claim is. Suppose you are given with an n of A with epsilon transition for L. So with a single initial state and a single final state. So how will you construct the n of A for L star? So we had seen a very similar construction. What you do is you add 2 epsilon transition like this. That's enough. So what is accepted by this? If you just take this path, what is accepted is L. And if you take only this path, what is accepted is epsilon, that is L raised to 0. And how will you accept L raised to 2? You come to this, that is L, go back like this, then again L square. Likewise, you can accept any string in L raised to I, where I is greater than or equal to 0. So in this lecture, we saw that regular languages are classed under string reversal, complementation, concatenation, and Kleene iteration. In the next class, we will see that regular languages are classed under intersection, union, and set difference. Thank you.